Hello students, and welcome to week 1 part 2, organizing quantitative data. In part 1 we learned the types of data and the difference between the two types of data and how to organize and visualize qualitative data. In this video I'm going to explain to you how to organize quantitative data, and we know that quantitative data can be discrete or continuous. So our objectives are to organize discrete data in tables, construct histograms of discrete data, organize continuous data in tables, construct histogram of continuous data, draw stem and leaf plots, draw dot plots, identify the shape of a distribution, and finally draw time series or line graphs. So one thing that I want to mention here is constructing histograms of continuous data. Organizing continuous data in tables is optional. You don't have to know how to do that because the process is a little bit tedious. The first step in summarizing quantitative data is to determine whether the data are discrete or continuous. We know that if the data are discrete, there are relatively few different values of the variable. The categories of data, which we call classes, will be the observations themselves. For example, if you have a range of data that spans between 1 and 5, let's say we're collecting the number of cars per household, that data is going to be discrete, and so the classes are going to be the observations. Let's say some of the observations are 0, 1, 2, 3, 4, 5. Then these are going to be the classes of our table, just like the qualitative data. So we treat it the same way we treat qualitative data. If the data are discrete, but there are many different values of the variables, let's say the range of the data, which is the difference between the maximum and minimum, is huge. Let's say we have data values, the minimum is 5 and the maximum is 100. That is a big difference, and we're going to treat it as continuous data even if the numbers look like they are whole numbers and they don't have any fractions. The categories of the data, which we call the classes, must be created using intervals of numbers. Here is an example of discrete data that is going to be treated like categorical data, and the classes are going to be the observations. The following data represents the number of available cars in a household based on a random sample of 50 households. We need to construct a frequency and relative frequency distribution. So you notice here the minimum is 0 and the maximum is, I think it's 5. So as you can see, we can basically list all of the numbers from 0 to 5 in one table and treat that as the class. So the first column here, which is the number of cars, is going to be the classes. And then we're going to tally the number of zeros we see in the observations, record the frequency, and we know how to compute the relative frequency from part 1. So we finish all of these, and I will show you how to do that quickly on Excel in a different video. So this is basically organizing discrete data in a table. That is a frequency table, and if you include the relative frequency, it's going to be a relative frequency table as well. After we construct the frequency tables for discrete data, we can create the histogram for the data. So the histogram is basically similar to the bar graph. The only difference is the rectangles or the bars touch one another. A histogram is constructed by drawing rectangles for each class of data. The height of each of the rectangles is the frequency or the relative frequency of the class. The width of each rectangle is the same, and the rectangles touch each other. So histogram is basically the visual representation of quantitative data And it's similar to the visual representation of qualitative data, which is the bar graph. So bar graphs are exclusively used for qualitative data. Histograms are used for quantitative data. So make the distinction clear. Here is the same example, and we would like now to create a relative frequency histogram. So instead of using the first and second column to create the histogram, using Excel, we're going to use the first and last columns to create the frequency, the relative frequency histogram. If we want to create the frequency histogram, we're going to use the first and second column. So let me just repeat that one more time because I think I messed it up. If we want to draw a frequency histogram, then we're going to use the first and second column. So the first column is the classes or the bins of the histogram, and the second column is going to be the height of each of these columns. If we want to create a relative frequency histogram, then we're going to use the first column for the classes or on the horizontal line, and then the relative frequency is going to be the height of each of the bars or the rectangles. So here is an example where we use the bins or the number of cars at the bottom, and these are called the classes. Sometimes we say those are bins. And then the height of each of the columns is basically the frequency of that column. So the first one, as you can see here, the frequency of 0 is 4. So you see the height of 0 is 4, and etc. And you see here the bars touch. So this is how we know we're talking about histogram and quantitative data, not qualitative data and a bar graph. In this example, you see the same exact thing. The difference here is the height of each rectangle is the relative frequency, or the percentage, you could say basically, or the probability of that category. So for example, if you look at the table, you'll see that the relative frequency of the first class, 0, is 0.08, represented in this height. So I was talking about classes. Classes for discrete data are basically easy. You just put all of the observed data without repetition, of course. So similar to what we did with qualitative data, categorical data, when we talked about the colors, we just listed all of the colors that we can see once, and we use that as our classes. In this case, when we have continuous data, the classes are different. The classes are basically categories into which data are grouped. When the data set consists of a large number of different discrete data values, or when a data set is continuous, we must create classes by using intervals of numbers. So let me show you an example here. The following data represents the number of persons aged between 25 and 64 who are currently work disabled. So you notice the range here is huge. It's not a number smaller than, let's say, 10. The range between 25 and 64 is big. So if it's more than 10, I would say we create, let's say 13, we create classes, we create interval classes. As you can see here, we created intervals for the ages. So the first interval is between 25 and 34. And then we counted the individuals in that interval, including the lower class limit and the upper class limit. So this class is the first class, and this number is the lower class limit of the first class, and the 34 is the upper class limit of the first class. We move on to the next one, and the next one here is, this is the second class, and 35 is the lower limit of the second class, and 44 is the upper class limit of the second class. The lower class limit of a class is the smallest value within the class, and I just showed you on this example which number is the lower class limit. So 25 is the lower class limit of the first class, 35 is the lower class limit of the second class, 45 is the lower class limit of the third class, and etc. While the upper class limit of the class is the largest value within the class. So 34 is the upper class limit of the first class, 44 is the upper class limit of the second class, and etc. The lower class limit and the upper class limit, we're going to use that to compute what we call the class width. The class width is basically the difference between two consecutive lower class limits or two consecutive upper class limits. For example, if I wanted to find the class width for these classes, I'm going to take 35 minus 25, that is the difference between two consecutive lower class limits, or I can say 44 minus 34, which is going to give me the same number, it's 10. So that is my class width. Here's a mistake that many of the students make when I ask for the class width. They just subtract 34 minus 25, which is in this case going to be 9. So that is not accurate. We use two lower class limits or two upper class limits that are consecutive. Let's look at this example. The following data represents the time between eruptions in seconds for a random sample of 45 eruptions at the Old Faithful Geyser in Wyoming. We want to construct a frequency and a relative frequency distribution table for the data. So I'm going to go with this one very randomly, but there is a process that we're going to follow, and I will include probably one example in your homework, but you don't need to answer that question if you find it very difficult. The smallest data value in the previous data was 672 seconds, and the largest data value is 738 seconds. We will create the classes, so the lower class limit of the first class, we're going to choose a number that is smaller than the minimum, or it is the minimum itself. The minimum is not a nice number. It doesn't end with 0 or 5. So I'm going to choose a smaller number that ends with 0, which is 670. The class width is, we're going to choose 10, random. Again, the class width is random here. And then we obtain the following classes. So if the lower class limit of the first class is 670, then we can create all of the lower class limits by adding 10 vertically. So we add 10, we get 680, 690, 700, 710, 720, 730. And then to create the upper class limit of the first class, we're just going to subtract 1 unit from the lower class limit of the second class. So we're going to subtract 1 from 680. We get 679. That is 1 unit here. When we say 1 unit, it depends on the type of numbers. If your numbers are 2 digits, 3 digits, the unit could be 1. If they are less than 1, the unit could be 0.1 or 0.01. It depends on the type of numbers that you are dealing with. If it's 4 digit, I would say 1 unit that you could subtract is 10 instead of 1. So now we're going to create the frequency tables and the relative frequency tables. We put our classes here, and then we count the numbers in our sample that are between 670 and 679, inclusive of those two numbers. Meaning, if you see any of these numbers, you're going to count them as well. And we have 2 values in our raw data in the previous slide, this slide right here. And then to compute the relative frequency, we divide by the total number of frequencies. We do that for each of the classes. So you see the second class doesn't have any. We don't have any numbers in our data. They're between 680 and 689 inclusive. We have 7 numbers in the third class, and etc. And then we add everything up, we get 45 frequencies, which is basically the sample size. Our sample size is 45 eruptions. And then we compute the relative frequency by dividing the frequency by the total number of frequencies, and we compute the answer. We get our proportion, which is also a probability, which is also a percentage of each class. The choices of the lower class limits of the first class and the class width were not following a specific steps, so it's very random. There is not one correct way to create, you'll hear me sometimes call them grouped frequency distribution tables. There isn't one way to create grouped frequency distribution tables for a particular set of data. It all depends on the number of classes you choose, which is usually we choose between 10 to 13, sometimes 5 classes. So it all depends on what we choose at the very beginning, which is the number of classes. And we can basically follow simple steps in order to create the same relative frequency distribution tables for one set if I give you the number of classes in advance. So if I gave you the number of classes, we might create the same relative frequency distribution table, but it's not wrong if you choose a different number of classes and create a different one. Some frequency distribution tables can better illustrate patterns within the data than others, so constructing frequency distribution tables is somewhat of an art form. It doesn't abide by any rules. You could say, unless I determine the number of classes for you, then you could follow certain steps and end up with the same tables. We usually use the distribution that seems to provide the best overall summary of the data. And when we say that, we mean basically it shows the distribution type of data, and we will discuss this later. For example, you can see here, this is not a great representation of the same set of data, and I can see here the class width is 5. So the reason why the class width is 5 is not working is because you see here I have an empty space, which is basically there are no values whatsoever in these classes, which tells me to increase the class width or lower the number of classes to begin with. Guidelines for determining the lower class limit of the first class and the class width, which is going to be the key to determine the entire table, is to find the lower class limit of the first class. So how do we choose the lower class limit of the first class? We follow these 5 steps. The first step is choose the number of classes. Usually this is given to you. Number 2, we're going to find the range of our data. The range is basically the maximum minus the minimum. Step number 3, determine the class width, which is basically the range divided by the number of classes that we chose. We're going to take the answer and round the number up to a convenient number. When we say a convenient number, we mean a multiple of 5 or a multiple of 10. Usually multiple of 10 is better. Step number 4, we compute this value, which is we take the minimum divided by the class width. The answer, we round that number down to a whole number. For example, if you get 20.3, we round it down to 20. If you get 20.9, we round it down to 20. And then we take the answer from number 4, let's say the 20, and we multiply it by the class width. Let's say the class width is 10. So it gives us 200, and that is going to be the lower class limit of the first class. In this picture right here, you see the data that we just worked on using a class width of 10. As you can see, the shape here is okay. It's nice. We don't have a lot of empty spaces. And then this is a histogram for the continuous data. As you can see here, the classes or the bins, they have a lower limit and an upper limit. So you can see here from the table, first table right here, the numbers are not the lower limit and the upper limit exactly, but they represent the lower class limits only, the lower class limits only. So to find the class width from the shape here, we basically subtract the big number minus the small number. So 680 minus 670, the class width is 10. So these numbers are all lower class limits. Okay, so that is a very important thing to notice. The height is the frequency of that class. This represents a class width of 5, which is the second table that I showed you, this one right here. And as you can see, there is a big gap, which tells us that the class width we're using here is not optimal. The next graph that we're going to discuss is the stem and leaf. A stem and leaf plot uses digits to the left of the rightmost digit to form the stem, and each rightmost digit forms a leaf. For example, a data value of 147 would have 14 as the stem and 7 as the leaf. So we determine the leaf first, and the remaining digits are going to be the stem of our data. Let's look at this example. An individual is considered to be unemployed if they don't have a job but are actively seeking employment. The following data represents the unemployment rate in each of the 50 states of the United States plus the District of Columbia in June 2008. And that is our data right here. So if we look at Alabama, which is 4.7, and we want to create stem and leaf. For example, if we look at Alabama, which is the unemployment rate is 4.7, 4 is going to be the stem, and the leaf is going to be 7. So we determine the leaf first, and then the rest of the number is going to be the stem. To create the stem and leaf plot, we put all of the stems in order without repeating, unless the leaf is very long. We put the stem in one column like so, and then we put the leaves for each of these stems. So 2 and 8 here represents the unemployment rate of 2.8. And then we go to the 3. So we have 3.8, 3.8, 3.8 3 times. If you go back to the raw data, you'll see that. And then we have an unemployment rate of 3.3, 3.9, 3.2, 3.9, 3.2, 3.2. So this is basically leaves. Those are leaves. And this is a stem. So we do that until we end up with the entire data listed here. So if I wanted to create the raw data, I will be able to convert the stem and leaf into raw data easily. Sometimes stems can be empty, and that's totally fine. Let's say if there is no unemployment rate that is 7 point something, we're going to leave that stem empty, but we have to list the stem anyway. So don't skip 7 and don't put 0 here. That is not quite organized because, as you can see, the leaves are not in order. So the next step is to order them from smallest to greatest, and that is going to look better. So this is how you're going to create a stem and leaf. Let's say one leaf is too long. We can basically split it into 2 stems and repeat the stem, and that is going to be okay. To summarize, to construct a stem and leaf plot, step number 1, the stem of the data value will consist of the digits to the left of the rightmost digit. The leaf of the data value will be the rightmost digit itself. Step number 2, write the stem in a vertical column in increasing order. Draw a vertical line to the right of the stems. Step number 3, write each leaf corresponding to the stems to the right of the vertical line. Step number 4, within each stem, rearrange the leaves in an ascending order. Title the plot and include a legend to indicate what the values represent. When data appears rather punched, which means some stems are very big or very long, we have a lot of values there, we can split the stems. The stem and leaf plot shows on the next slide reveals the distribution of the data better, as with the determination of class intervals and the creation of the frequency histogram, judgment plays a major role. There is no such thing as a correct stem and leaf plot. However, some plots are better than others, just like relative frequency tables for continuous data. You see here we split the stem of 3 to 2 categories because it was big, it was long, and the 4 and the 5 and the 6. So instead of including one long stem, we split it into 2 stems. to represent the data a little bit better. One of the advantages of stem and leaf over the histograms is once a frequency distribution or a histogram of continuous data is created, the raw data is lost usually. We can't go back and recreate the raw data from a histogram or a frequency table. However, raw data can be retrieved from a stem and leaf, just like I showed you previously. Another plot that represents quantitative data is what we call a dot plot. A dot plot is drawn by placing each observation horizontally in increasing order and placing a dot above the observation each time it is observed. Sometimes we just represent the highest dot only and remove all of the bottom dots. Sometimes we include a dot for each observation. So here is an example that, as you can see here, this is the data that represents the number of cars available in a household based on a random sample of 50 households. We need to create a dot plot for that data. So as you saw, the observations we observed are 0 cars, 1 or 2 or 3 or 4 or 5 cars, and then we placed a dot each time we saw a 0 number of cars, and then we placed a dot each time we saw 1 in our raw data. Sometimes you don't see all of these dots, but just the highest dot, the top one, that represents the highest number, or the number of observations. For example, instead of seeing all of these 4 dots, you just see the 4th one. That's also a dot plot represented differently. Why do we discuss the graphs and the representation or the histogram of the data, or the stem and leaf, or the dot plot? These graphs and representations, visualizations, help us identify the shape of a distribution. For example, a uniform distribution is basically the frequency of each of the values of the variable is evenly spread out across the values of the variable. Bell-shaped distribution, the highest frequency occurs in the middle, and frequencies tail off to the right and to the left of the middle. Skewed to the right, the tail to the right of the peak is longer than the tail to the left of the peak. Skewed to the left, the tail to the left of the peak is longer than the tail to the right of the peak. And let me go back to the dot plot and let me show you what I mean by that. So if you try to create a trend here at the top of the dot plot, you will notice a trend here, which is, I tell you, this is approximately bell-shaped. There is a peak in the middle, and there are approximately equal tails on both sides of the peak, which is right in the middle of my data. So this data is going to be bell-shaped approximately. I can do the same thing with the stem and leaf if I lay it down with the stems horizontally. I can do the same observation with histograms. So draw a trend line and see what shape you get. This is approximately bell-shaped. I would say it is a little bit skewed to the right because this tail is longer, but it is, to me, approximately normally distributed. And here are the distributions I talked about. You notice this is a uniform. The frequency is the same for each of these bars. This is approximately bell-shaped. The bulk of the data is exactly in the middle with almost equal tails to the right and to the left. This is skewed to the right, the bulk is to the left, and then the right tail is longer than the left tail, so this is skewed to the right. This type of data, you notice here, there is a bump here, and then the tail to the left of the peak is longer, so this is skewed to the left data. This helps us later on in our studies, especially the bell-shaped is going to be studied throughout the semester. So it's very important to determine the shape of your data. If you look at this shape right here, which represents the time between eruptions at Old Faithful, In seconds, I can tell you this is going to be skewed to the left because here is the peak and there is a tail to the left. So here is an activity that I really want you to read, and I want you to choose one of these activities or all of them, and then I want you to answer the questions. This is going to be part of your discussion activity. So I'm gonna just read it really quick. You can pause the video and you can read it, or you can go download the PowerPoint which is available on D2L, and you can do one of these activities or all three of these activities. I want you to answer A, B, or C. So choose from A, B, or C. I want you to answer D. And then if you did all of them, I want you to answer E. So we saw in example 0, I hope that you watch example 0, how to use Microsoft Excel to generate random numbers. Use Microsoft Excel, randomly generate 200 integers between 0 and 20, inclusive of 0 and 20. This is the integer can be any value greater than or equal to 0 or less than or equal to 20. That's what we mean by inclusive. And I want you to store these values on in your spreadsheet. Activity number 2, choose 20 people randomly and determine their resting pulse rates. If you're a nurse in the health sector or plan to be a nurse, you could do this activity if that is something that interests you. Collect these data from the 20 people and store them in your spreadsheet. Ask 30 people how many people live in their households. You can choose that randomly, your neighbors, your friends, anybody. You can just collect 30 random answers from people. Collect the data and input them into your spreadsheet. Now, the questions. What shape do you expect the distribution of random integers to have, and why? What shape do you expect the distribution of pulse rates to have, and why? What shape do you expect the distribution of household size to have, and why? Draw a histogram of one data set. For the random integer data, use a class width of 2. If you did all of the activities, what shape did each have, and are you surprised by your findings? Let's see all of that in the discussion that I'm going to post on D2L. So go ahead and try this activity out and let's see your answers. I can't wait to look at your discussion. The last graph that we're going to discuss is time series or line graphs. If the value of a variable is measured at different points in time, the data are referred to as time series data. A time series plot is obtained by plotting the time in which a variable is measured on the horizontal axis and the corresponding value of the variable on the vertical axis. Line segments are then drawn connecting the dots or the points. And here is an example. The data to the right shows the closing prices of Dow Jones Industrial Average for the years 1990 through 2007. And to plot time series, you're going to plot the years on the horizontal and the values, the closing values on the vertical, and then plot each dot and then connect the dots together with lines. This is what we call line graph or time series graphs. So this concludes part 2 of the first week. If you do have any questions, feel free to contact me. I will have some virtual office hours if you can't make it on campus, and I would love to have you on campus if you can make it to my office. All of the students' hours are posted on D2L. Also, they are posted in the syllabus of the course. Please, if you're having difficulties with the material, come see me or schedule your virtual meetings via WebEx. So I'll see you either virtually or I'll see you in person. If you need any help, I'm here to help you. I'll see you in a different video.